Morning. Get started. I think I had announced to you that we weren't going to do 3.7 or 3.8. I think we need to do 3.7. I've made a little change there, which means that all that projected stuff is going to be one day off, or one class period off. So I believe I had said today was going to be review 1, Friday was going to be review 2, Monday was going to be test. Now it appears that we're going to do 3.7 today, review 1 Friday, review 2 Monday. So instead of the test being Monday, now it's going to be Wednesday. I had originally said the test would be Monday. Now I'm saying it'll be Wednesday. Sorry if that was confusing. Because 3.7 is kind of a summary of about, like, all right, why did we do all this second derivative stuff and everything? We really haven't made practical use of it, so 3.7 we will. Yeah.
Can we get, like the test you gave us last time, can we get one of those again?
I don't know. I'll have to, we'll see. I'd like to. I honestly don't know if I'll have the time, but I will. I'm glad to hear it was helpful. Okay. One of the problems with this one is I'm not sure I have a test from chapter 3. I'm going to have to look. Okay, well that you definitely have. That's like the assignment. But I get what you're saying. You're saying anything similar to a real test is helpful. So maybe what I could do is just write 2 tests and give you 1 for review. I don't know. The only problem with that is I don't know if we're really going to have enough time to evaluate a practice test in advance, but let's see. And to really make that useful, you really need to get your hands on that, I would say, by Friday, by next class. Or we have a Thursday class in there too, I know. But Friday for sure, I suppose. So I don't know. That's going to be, the only issue is, do I have the time to do that? I'm going to write myself a note and try. I think you're right. I got positive feedback from others also. So kind of like a practice test is what you're saying. Let me ask you this. How would you rate wasn't there like a practice test in here? Or am I wrong? I know there was a review, but was there like a test? No, just a review. At the very least, I might do this to satisfy you. Well, I mean, come on, guys. To satisfy this class, maybe what I could do is take the review and isolate it down to about 7 or 8 questions that I would really like to ask on my test. And if nothing else, I could say, when it comes to the review, target these 8. Maybe that's a little more doable. I'll give that's an idea that might make it workable. Okay. Good thought. Okay. Let's go on. Questions on, let's see, last time we did what? So we're still skipping 3.8. It's just that we're not going to skip 3.7. Questions on asymptotes? Yes. 27. Okay, 27. I got to get my head into the problem first. You were supposed to find the limit on that one? Okay, and it says find the limit of 5x squared over x plus 3 as x approaches negative infinity. Okay, as x approaches negative infinity, the top will get incredibly large positively, because a negative squared is a positive, and then a positive times 5 is a positive. On the bottom, you got this, you're going to have a big negative. And,
Why is it because of the negative?
no asymptote. Why are you talking about asymptote? And maybe I'm looking at the wrong page.
Or no limit, sorry.
Oh. Well, okay, so let me just finish up where I was. So you got a large positive on the top and a not as big negative on the bottom. So it's a larger 1 over a square, not as big, it's going to be number 1 large. And it's positive over negative, so I know it's going to be negative. So the answer is a negative large, negative infinity. Now, in effect, but to answer your question, when you say if there's any infinity in a limit answer, in effect you're saying there's no limit. So it's kind of ironic. When we write down infinity as either negative or positive, as the answer to any limit question, we're really saying, it's so huge I can't give you the limit, but I do know it's negative or positive. You know, that's about the only thing good out of those crazy things is it's got a sign in front of it. And that means it's, what, way down there? But in effect, you're, like I said yesterday, you're kind of waving the white handkerchief and saying, okay, I can't give you a number, but I do know it's huge negatively. So, there's some good to it. Yes? All right, 55 from 3-6. Sketch the graph. Use intercepts, extrema, asymptotes as sketching aids. All right, let's see what we got. We have the equation 2x squared minus 6 divided by x minus 1 quantity squared. So we're supposed to do what we can to sketch this thing. Okay, the first thing, actually this is so much like what we're going to be doing for the new lesson. It's actually a really good intro also to the new lesson, so I'm glad you picked that one. I mean, a lot of them would be good. Let me ask you this, are there any domain issues here? Is there anything that could cause this equation to, so to speak, crash? And the answer is yes. I can't have x be 1, right? I can't have x be 1. So let's just write that down right off the bat. X cannot equal 1. That probably means we have an asymptote there, almost for sure. Okay, we got that noted. Now, let me ask you this. What are there, I would right away think, are there any, before you even do any derivatives, the question is, when will, I don't know quite how to write this, so I'll just write it out in words. What are the zeros of the function? You guys remember that terminology? What does that mean? It means when is the function equal to 0? So in other words, I want to know when it crosses the x-axis. That would be interesting for graphing. So all you have to do is set the function equal to 0 and do your best to solve. Well, in this case, we could multiply both sides by x minus 1 squared, and then we just have 0, you know, it's goodbye denominator. Then you'd have this, and we could solve for x. 2x squared equals 6, x squared equals 3, So it looks like there's two places where the graph will cross the x-axis. Plus square root of 3 minus square root of 3. So those are interesting points. And in fact, maybe we should start collecting some of this on a graph. Let me see. Let me pull up a... Let me get a grid here. I guess this is the... Sorry. A little slow today. Okay. So let's already mark on the graph what we know. We believe there's a vertical asymptote at x equals 1. So let's indicate that with a dashed line. We believe we've found a couple zeros of the function at plus or minus the square root of 3. So that would be, what is that, 1.73 or something like that, the square root of 3? Is that right? I wonder if my memory is right. Thanks. 1.73. I maybe should have made this bigger, but that would be about here, and that would be about there. Okay? All right. Now it's time to do the derivative investigation thing. So let's extend this and work on the left side here. All right, the functions up here was equal to f of x. So what's f prime of x? Quotient rule? I'll use the quotient rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator Let me explain what I just did there. I did the power rule. I took 2 times this to the first, and I multiplied it out. Chain rule, yeah, but it's a 1. So, sorry I didn't have room there. Let's carry this out a little bit further. I suppose we should probably... I'm trying to think if we should simplify this or not. Yeah, I think so. And then this minus parentheses 2x squared times x is 4x cubed. 2x squared times negative 2 is minus 4x squared. Minus 6 times 12x. And minus 6 times minus 2. Okay? What is this thing here? 4x cubed minus 8x squared plus 4x. So bringing everything together, I have 4x cubed minus 4x cubed, so the cubes are gone. I have negative 8 squared minus a negative 4x squared. I have positive 4x minus a negative 12x. And I want to subtract a positive 12. Okay. All right. When is that equal to 0? We could divide through by 4. Actually, let's divide through by negative 4. Then we'll have a little bit nicer quadratic to work with. That'll give us x squared minus 4x plus 3. And that's factorable, isn't it? X minus 1, x minus 3, yeah. And of course there are 2 times when that will happen. Okay, what do we call those places? Did I make a mistake? I didn't do the denominator, did I? Yeah, you are correct. That's a major error, and I apologize. And I didn't, I'm only laughing at, I'm mocking myself, okay? Yeah. Yeah, that's what I did. So this is all correct. Up to here, I just need to put it over my denominator, don't I? Sorry about that. Actually, still might be able to make use of that other stuff. But, so actually I will. It's actually not going to affect the problem. Yes. Did I make another mistake? Yes. Oh, okay. So when I was doing the derivative of the denominator, what's the derivative of this? First you use the power rule and you say 2 times x minus 1 to the first. And then the chain rule would say multiply by 1. And that's why I didn't write it down. So I believe that I actually did right. But then when you take 2 times the quantity x minus 1, yeah. You know, it's ironic. My answers were still right. Talk about pure luck. Here's what I should have had in the denominator. Now, when you set that equal to 0, what's going to happen? You multiply both sides by the denominator, and you actually get what I had here, which is 0 equals the numerator. So I'm not going to write that down again unless you want me to. It's still actually 0 equals, comes down to 0 equals x squared minus 4x plus 3. And that really does come out to x equals 1, x equals 3, because it's the factoring is x minus 1, x minus 3. So, anyway, by accident, I had it correct. Totally by accident, because I forgot a very important thing. Now, what do we call places where the first derivative can be equal to 0? Critical points, right? So, what does that generally mean? It means we got a horizontal tangent line, and it's either a relative min or a relative max. So I don't quite know where those are, but according to this, it's obviously 1 isn't going to work because we already know there's an asymptote there, but at 3, something special is going on, which would be somewhere along here. Okay. I don't quite know where to put those. Maybe we could do this. What is the value when x is 3? Going back to the original function, what's the y value? Let's do it. What's f of 3? 18 minus 6 is 12 on top, and 4 on the bottom. So it's 3. So 3, 3. So at the point 1, 2, 3, 1, 2, 3, right there we have a horizontal tangent line. I don't know, I'll tell you what, I'll use a green. That's probably too big, but I wanted to use something other than a black line because the black line's for the asymptote. So we know we have a horizontal tangent there. Okay. That tells us I shouldn't have really... Yeah, okay, so let's see what happens. So most likely what's going on there? Probably this, right? Because we know we're before it. Should we look at... we're supposed to, this is a lesson about both derivatives, so we should probably... How bad is our derivative? It's not real pretty. So I don't know. What else would you like me to do to get ready for sketching? Did you want me to do the second derivative? Horizontal tangent? Yeah, we just found one. Oh, is there, okay, that's a good question. Let's analyze the original function. Okay. Isn't this really x, on the bottom, isn't this x squared minus 2x plus 1? Now, do you remember the little analysis tool I gave you for horizontal tangents? As x gets really, really big, what's going to happen to 2x squared over x squared? Because the powers are equal, there's going to be a horizontal asymptote at the ratio of the coefficients. So there should be a horizontal asymptote at 2. And I better use a black line for that. So, you know what that's telling me? When we get way out here on the right, this thing is going to come back and approach this line. So, you see what's happening here. We're getting something that looks like this. You know, something that, or it might cross and come back from the bottom, but it bumps on 3, makes a relative max, and then when it get way out there, it approaches the horizontal line too. Good question. And we've got this vertical asymptote. We still don't know what's going on over here. I don't know. So should we just take a look at the graph now, or do you want to analyze it some more? These can take quite a while. Let's see what we got from the graph. So this time we've got numerator 2x squared minus 6 divided by parentheses x minus 1 squared. You can see we had that part of the graph analyzed approximately correctly. You can see our vertical asymptote there of x equals 1. You see how we did go up and hit a bump there? And now when we go way out here, we're approaching that horizontal asymptote. The only thing we really didn't look at is what goes on over here. So our analysis tools really did give us some good information about the graph. And that's more of the same as what basically we are going to be doing for the new lesson. Yeah.
You don't have to answer it, but how would you find the left side?
Well, I've plot a couple points. Actually, you know something, there is one point we have up here that I never made use of. Remember I had the 0 over here at negative square root of 3? Remember that? Negative 1.73? I had it marked. Here it is. So we had that point. You know, we knew we had a vertical asymptote at 1, so I would have picked a point like, what happens when x is 0? That's a real easy one. Look at the function. What's x equals 0? Let me just put this away for a second. What's f of 0? On top we get negative 6, and on the bottom we get 1, and negative 6 over 1 is negative 6. So at 0, 1, 2, 3, 4, 5. So we knew we had that point. So now I could see, oh yeah, that makes sense. And then I think, Darnell, I would have just picked a point like, I don't know, negative 8. And then you would have seen that that was going to be up here. And then you'd get, now you got enough. The other thing we could have done, I'm a little bit conscious of time here, is if we did the second derivative. And if we found out that the second derivative was negative all over here, that tells me for sure this thing is curved, cupping downward, and that would have confirmed, yeah, this kind of curvature is definitely correct. Those would all been things we could have done. You know, we never did this. There's one other thing we could do. What's the limit of this function as x approaches negative infinity? We did the positive infinity. If x gets negatively huge, we're still going to have this ratio of 2. On the top, it's going to be positive, because a negative number squared is positive. Oh, it's going to be positive on the bottom, too. So it looks like this is going to approach x equals 2. So I should have really made you know, it's going to approach this same bar over here. Can we see that in our graph? So there is one additional, yeah, you can't, maybe if I shove it over, you can see how it's flattening out and getting closer to 2. So to be more exact, we've got a horizontal asymptote of 2 on both ends. This one, it comes at it from the bottom, and the other one, it comes at it from the top. So those graphical tools help you with these kind of strange looking creatures. I shouldn't say strange. Oh, yeah. This is not your run-of-the-mill algebra 2 function. You've got some interesting bumps and asymptotes. So anyway, that was a good question for a bunch of reasons. I think I want to show you some things, and then we'll see if maybe we can do more questions. The only trouble with these questions is they're pretty time consuming, and we could easily consume the whole class with a couple questions, which is not necessarily a bad thing. This is the title of 3.7, and it's what we just were doing. It's saying, oh, let's take all these tools and use them to help us sketch curves. Well, that's what we've already been doing. I wanted to show you the tools they used in the book because I think they're worthy of looking at. You guys are probably better off. This is kind of tiny up here. If you just look at, this is on page 232 of your book. Okay? This is the top part of the page on page 232. It says, hey, analyze the graph. First thing I would do is find out just like I just did with the one she gave me, when can the function be equal to 0? If it's not too hard to find out. Well, they factored it, thankfully, because it's a little bit of a beast to factor. Here it is, x minus 1 squared times the quantity x plus 5. Can you see now, what would make this equal to 0? Well, if x is 1, that would. Okay, so 1 is a key point. That's a 0 of the function. And -5 also causes it to be 0, right? So factoring really exposes that. Now here's a cool thing. I don't know if you remember this from your algebra class, but whenever a root has a multiplicity that's an even power, like here, this is a multiplicity means there's 2 roots of 1, aren't there? X minus 1, x minus 1. So 1 appears twice. That is a bouncer. In other words, at 1, this graph will bounce off the x-axis, and sure enough, it does. Here's the graph. And when you have a odd multiplicity, like here, we only have 1 root of -5, then it crosses the x-axis at that point. I don't know. If you never had that, don't feel terrible, but those of you that did have it, you really got an advantage there, okay? So when roots appear an even number of times, you've got what I like to call a bouncer. We don't know if it's from above or below, but it hits and glances off. When you've got an odd number of roots of that, it crosses. Okay. So already we got some kind of cool things. Time to take the derivative. Find the first derivative. It's factorable. Set it equal to 0, and you can see there are 2 critical numbers. I'm sorry, yeah, 2 critical numbers. X cannot be 1, and X, I'm sorry, I shouldn't say cannot be. A critical number is when X equals 1, and when X equals -3. What does that mean? There's probably a horizontal tangent at those values. And sure enough, at 1, you can see we do. And at -3, it's going to be the top of another hump. Okay, we got our critical numbers. So, what numbers have we identified? Where the function is 0, where the first derivative is 0. I would do one more thing, if it's not too hard, and that is find the second derivative and find where that's 0 also. They did that here. Turns out to be a pretty easy derivative, 6x plus 6. And when is that 0? Only one time, when x is negative 1. So what's so special about the second derivative being 0? That's a possible inflection point. Sure enough, look, at negative 1, the curve is changing from one concave to the other. So what they did now, so what did we do? We said, when is the function equal to 0? When is the first derivative equal to 0? And when is the second derivative equal to 0? Those are all special points. Then they just made a chart and said, let's summarize what we know about this thing. Take a look at the chart. Can you make sense out of that? It's saying, all right, negative 3 was special where? Well, that was where we had the first derivative, where we have a horizontal tangent, most likely. So what did they write in here? At x equals negative 3, the slope of the tangent line is 0, or the first derivative is 0. Where did they get this from? What's the y-coordinate? They just went back, took the equation, and plugged in negative 3. Comes out to 32. Okay. Now, how did they know this was a relative minimum? All you got to do is take negative 3 and plug it into your second derivative formula. What's f double prime of negative 3? Negative 18 plus 6, negative 12. Negative! That's the key thing. Negative tells me concave down. And therefore, I read this wrong before. I said minimum, it's relative maximum. Concave down means it must be reaching a high. So that's where they got this text. Okay, well, you keep going. You take all your points, and we pretty much, I did it verbally, we pretty much described what the graph looks like. By now, it's pretty easy to go in there and just... And what I'd love you guys to do is just kind of make your rough sketch, then maybe do it on the graphic calculator, compare the two. Hopefully we got a match. Let's look at one that's a little bit harder. This one, same deal. This time, the function is, this is, by the way, this is example 5, and this is in your book on page 236. And you see how we have these fractional exponents. 2x to the 5/3 minus 5x to the 4/3. Well, derivative-wise, they shouldn't give us much grief. The only thing that makes it harder is, what in the world is that thing shaped like? Well, let me ask you a question. What does it mean when you have a fractional power? What does the denominator mean in a fractional power? In this case, what's the 3? The 5/3. What's that 3 do? The top is, we got a fractional exponent. The top means power, and the bottom means root. So this is like taking something to the 5th power and then taking the cube root. Or first taking the cube root and then doing it to the 5th. It doesn't matter which order. What do cube roots look like? Well, that's like a S, isn't it? You know how cubes do this. Well, a cube root's that same thing, only kind of turned on its side. So we know we've got one of these kind of like S curves, most likely. We got one cube root minus another, although there are, I'm not ignoring the numerators. All right, so maybe the first question is, can we do it? When is this function equal to 0? When will this be equal to 0? Can you see it? Well, wouldn't 0 work? Because what happens when you take 0 to any power? 0. And 0 times 2 is 0, and 0 to any power is 0, and 0 times 5 is 0, and 0 minus 0 is 0. So the point 0, 0 appears to be on our graph. That's important. So we got an intercept. Okay? Let's look at the, is there anything that you can't have in the domain? Is there any kind of number you can't take a cube root of? You know, we already know there's certain kinds of numbers you can't take a square root of, but how about a cube root? When you're doing it, what, an odd root like that, 3 or 5 or 7, you have no problems because you can do, like, is there a cube root of a negative, for example? Yeah, negatives are perfectly okay. And square roots, no, we couldn't. So, it looks like it's pretty wide open. We don't have any domain issues. All right, so probably there's no asymptote that way, and it's probably nice and connected. We don't have to deal with that. We already know we go through the origin. Let's find the first derivative. They do that right here. You look up, you can probably look in your book, you can see it better. Actually, they write it two ways. I like this factored way right here. Because when you look at this, can you tell when is it that this thing will equal 0? Well, it looks like, first of all, wouldn't this, if x was 0 out here, wouldn't that make it 0? And right here, wouldn't it just be 8? Because what's the cube root of 8? 2, and 2 minus 2 is 0. So it looks like we got two of them, at 0 and 8. Okay, so what does that mean when the first derivative is 0? It means we probably, you're not positive, we probably have a horizontal tangent. Well, they went on, found the second derivative, found out when was that was 0, and you can see they developed this chart at the bottom of the page. And by the way, they give you a caution here. I'm not really into TI calculators, maybe as much as I should be, but they mention here in this box that some graphing utilities will not graph the function in example 5 properly if you use the fractional x, you know, if you say to the power 5 divided by 3, you may have to, you're going to have to find that out on your own. I did graph it. I did graph it using this tool I use up here, and you can compare that to the graph in the book. It looks, I don't know, did yours? Were you guys able to do it? I guess what it's saying is sometimes fractional powers don't quite act like roots. So did you get, if you get a chance, plug it in, see if you get something that looks like that. By the way, this almost looks like the top of a pump, doesn't it? But if you look at it closely, it's actually a point. And so there's really, got kind of a weird thing going on right here. But did you guys get a graph that looks something like that? You didn't have any problems? Okay, so it's obviously not the TIs. But some calculators evidently will go a little bonkers, and they give you a suggestion. They say, okay, go ahead and do it this way. First tell it to do the cube root, and then tell it to take that to the 5th. So I don't know if any of you do have non-TIs, you might want to consider that. All right, should we try, in the remaining time, let's at least get started on a problem. And the one I thought we'd do, 30, try to do 37. Okay, so here we go. We probably won't have time to finish, but... Okay, number 37 has this function. Okay, x times the square root of 4 minus x. Are there any domain things here? Is there anything x cannot be in the domain? It can't be bigger than 4, can it? Because if x is bigger than 4, we've got the square root of a negative, which is a problem. So, wouldn't you agree that x has to be what? 4 or less? Is it okay if x is a negative? Yeah, because what happens when you subtract a negative? You actually wind up adding. No problem. All right, so this is kind of interesting. The graph, according to this, never even gets to the right of 4. Okay? Let me ask you this. When is the function equal to 0? So these are the zeros of the function. This is easy. Tell me, when is that equal to 0? One of them is when x is 4. So, you know what I should do is let's just write this point down. Yep, when x is 4, y is 0, and isn't it also at 0? Just easy one out here. When x is 0, isn't this whole thing going to multiply out to 0? Okay, so we got 2 zeros. So now we got a couple points on our graph. Cool. All right, we've kind of milked that. Let's work on the derivative now. First derivative. Okay, product rule. And, you know, I can think of this as what? X times the quantity 4 minus x to the 1/2 power. Okay, product rule. The first times the derivative of the second. See why I have that -1 in there? Because of the chain rule, right? Plus the second times the derivative of the first. Well, that's just a 1. Okay. Simplify. We got, let me know if, let me write it down and you can let me know if you see where I got it. So see if you can tell where I got that. First here, I just took the -1 times the x times the 1/2, and that gave me this. And then this means square root in denominator. So to simplify this a little bit, should we get a common denominator? So let me change colors here. So what you want to do is get 2 times square root of 4 minus x on top and bottom. So I'm going to multiply top and bottom by that. And what does that give us? Common denominator. This is going to be -x. And over here, square root 4 minus x times square root 4 minus x is 4 minus x. And doubled is 8 minus 2x. Bring it together. Okay, So there's our first derivative. Now, when is that equal to 0? Well, wouldn't you multiply both sides of that by 2 times the square root of 4 minus x? And then you'll have this in your next line. And then you can just solve fairly easily. What do we call it when we find a place where we have a 0 first derivative, critical point? It's most likely what? Either a high or a low. So, and you know, we should probably, I'm not going to do it right now, but you could also calculate the y-coordinate. Just plug in 8/3. So that's a critical point. Okay. Then the next step, find the second derivative. Anyway, I'm running out of time. But what I'll show you, I worked out the graph for this. That is this one. Talk about a unique graph. There she is. And let's just see a couple things already wacky between the eyes. Like, you notice how the graph never gets to the right of 4. That was what we predicted because of the domain. It just kind of stops. Also, we found a critical point at, what did we say, 8/3? What's 8/3? 2 2/3? Sure enough, at 2 2/3, we do have a critical point. We didn't have time, but had we gone on and found the second derivative, we'd have found that it was forever negative. Meaning, this thing is always concave down. And you notice it is. It's always shaped that way. So the idea here is you can now pursue a bunch of strange new functions using all of these nice calculus tools. And don't forget about your cool algebra tools. I've got 6 problems listed. I'll tell you what, you only have to do 5. Okay? So there's a list of 6 here. Do 5 of the 6. So these take a while, so it makes sense that we should do less. It's on the website too.